Thank you, folks. This is the same presentation I did during Siggraph in Denver a few weeks ago. This is a very practical presentation, very hands-on. So I did it in a way, so you go to the GitHub repository, you get the PDF there, and you follow slide by slide, because there is a lot of content a lot of the time in some of the slides. But the idea is that you learn how to truly make the render pipeline your own from scratch. So we're going to cover the first half of the presentation, which will give you learn even all the way about, for example, how to render the meshes that you add in the editor to your entities, and how to fully render those meshes exactly the way you want it, with the exact shaders you want in the sequence you want, and so on. So basically, you're going to basically replace the whole render pipeline that comes by default with the engine. So for those who don't know me, I've been around with the code base of O3DE since the days of Lumberyard in 2018. So yeah, when I joined the Atom team, I was mostly in charge of the shader build pipeline and the shader compiler, to be more precise. And after time, then I became more, lately in particular, I've been working mostly on the OpenXR and Vulkan stack on my day job. For those who not too familiar with O3DE, even though this presentation is focused on is a very like Hello World style of presentation, suffice to say that this is a AAA render AAA engine that is ready not only for games, but also some companies use it for robot simulation, can be used for anything related with real-time AAA quality. And here, of course, a brief summary, like what you can do during development. You can do, in development-wise, you can work on Linux or Windows. Even during development, you can work with OpenXR, which is based on Vulkan. And for the runtime, of course, Linux, Windows, Android, macOS, iOS, and also OpenXR via Vulkan. So in the agenda, this is the original agenda. We're going to stop at the end of number 5, which is Hello World Mesh. Even though it says Hello World, you're actually going to be rendering the real meshes that you typically design your levels with. So it's going to be very meaty for that first half. And hopefully in the next Connect, we can go through the second half, which requires a little bit of C++ and so on to do even more customization of the render pipeline. And of course, the target audience is that even though you may not be familiar with O3DE, you're familiar with engines, how they work in general, and especially some familiarity with the 3D graphics stack. In particular, understanding the concept of attachments versus resources. When a resource is an attachment, and what is the key idea? Because attachments are things that you can actually write to, and because of that, it requires synchronization between passes, so they are a very special kind of resource. And those concepts are essential so you understand the material that I'm about to present. And this is the GitHub repository. It's all there. You can try it, and the PDF is also located in there for this presentation. So in the big picture of how the engine and the renderer work together, you have at the highest level, you have the game logic and the data. At the next level, you have, in terms of rendering, and all of those components that live in the game logic talk to either the material system or the RPI system, and a combination of those. So we're going to learn about that square on the right, where we can basically, we're going to bypass the material system and talk directly to the RPI. And of course, the RPI talks to the RHI, and the RHI figures out whether this is DX12, Vulkan metal, and eventually send data to the GPU. So the big picture of O3DE is that at the high level, you're going to have components. This is the things you see in the editor when you drag entities and you add components. Then below those components, in the moment we talk in terms of rendering, each component typically talks to a feature processor, whether it is your own feature processor or another somebody else's feature processor coming from another gem. For example, the mesh feature processor typically gets mesh data from a mesh component, but you could develop your own component and send and create message leveraging the mesh feature processor. So it's up to you how you want to combine these things. But in general, for every rendering related component, there is a feature processor that really takes the data in that component and sends it, transform that data into what is called draw packets and draw items, and set that data to the views, which eventually, whatever is the active render pipeline, each pass is going to fetch data mostly using an address, and that address is called the DrawListTag. And based on that, a pass know, oh, these meshes, this geometry is for me. I'm going to create command list and so on, and give it to the RHI. So in general, when we talk about render pipelines, we're talking about that bottom section where you see all of the passes. And you can instantiate a series of passes, which is a pipeline, with an asset, or you can from scratch write C++ code and create a pipeline. But again, that is there are very rare cases you're going to need to do something like that. What you tend to do is mostly you have an asset and then you customize it, some parts of it with C++. But for the most part, you just have one asset, and there is no performance difference between using an asset or doing C++. And on another interesting thing here is, regardless whether the pipeline, whatever pipeline is loaded, at the top section, you see still the components which talk to the feature processors. A lot of the time, the feature processors are always registers and running in the system. And you could have render pipelines with passes that none of the feature processor recognize. And a well-written feature processor will check for the passes they care about, and maybe they say, oh, you don't have even this pass in the current active pipeline. I'm just gonna shut off myself and do nothing. But keep in mind that feature processors that are, when you compile and you have gems and all of those things, all of the feature processors that come with those gems are gonna be active, but not necessarily will be doing any work if there is not a pass or a render pipeline that is ready to talk to that feature processor. So keep that in mind. And also, the first experiment you can do in this presentation is you can replace the main render pipeline, let's say with the mobile render pipeline, just with that command line that is highlighted on the top right, -- render pipeline path. And you can see on the editor, when you run it, you're going to see at the top right that what is the active render pipeline. So just by doing that, you already customize the render pipeline. Of course, in this case, you're leveraging the mobile pipeline. This is great also because that means you can develop for mobile and do 90% of your work on desktop, because on the desktop, you're going to see exactly, you're going to be running the exact same pipeline that is going to run on the phone. So it gets you, 90% of the work done just by doing that trick. Okay, so the first thing about enabling a render pipeline is basically, this is an asset, which is basically typically officially called a render pipeline descriptor. And it has the extension AZ asset is a JSON file that describes a directed acyclic graph. So on the previous picture, you can see these passes kind of running in parallel in that picture, but that picture is a little bit misleading because in real life, most of those passes are interconnected through attachments. And thanks to those attachment dependencies, the RPI and the RHI work together to create a frame graph. that eventually knows exactly what is the exact sequence in which each path is supposed to run. Also, because a render pipeline is an asset, this asset is going to reference past classes. And you can only, of course, reference past classes that are registered with the renderer. So to know what past classes are available, you look for past factory, add past creator. As an example, you look for past factory, add core passes. And by grepping those strings, you can figure out what are all of the passes that are active or registered that you can leverage in your render pipeline assets. So hello world triangle. So the first thing we're going to do is we're going to replace the whole engine main pipeline with a very simple pipeline that only knows how to render one triangle. But to make it interesting, through assets, you should be able to customize the background color, what is called the clear color of the screen, and also the color of each triangle, of each vertices. And then without recompiling or restarting the editor, you just change an asset, you change the colors, and automatically you should be seeing reflected in the screen. Anything else you're going to do with the editor is not going to be reflected, because typically it is the main render pipeline who renders, debug text and auxiliary geometry. In this case, you're not going to see even the gizmos or anything. So what are the basic steps to create a very simple pipeline? So the first thing is that we need to have an asset, a shader asset. This is what we call the shader code, the vertex and pixel shader. Then, of course, we need what is called the shader file, .shader, which is basically a file that defines the entry points. Basically, with this file, you say, this is my vertex shader, this is my pixel shader, entry points, some blended states, and also compilation options. Then we're going to create a pass asset where we're going to define basically what kind of attachment this pass requires and so on. And then we're going to create the pipeline. And this pipeline is basically the parent pass. And this pipeline is going to reference the one triangle pass. So basically, we're going to build a one pass pipeline. And then we're going to create a render pipeline descriptor asset. And thanks to this asset, we're going to be able to give it to the command line as a starting parameter, and we're going to be able to replace the render pipeline of the editor in this case. And also in this case, also even if you build like a launcher or a game client, that game client should also be able to use that same pipeline too. So the first step is the shader code. And this is like a compressed version, because if you go to the original file and you're going to see the links, and you're going to see a little bit more comments and so on. But suffice to say that you have a main, a vertex function, a vertex shader function, where basically it just gets the position, which are supposed to be in clip space coordinates, and the color of each vertex, which is coming from shader constants in this case. And of course, the pixel shader just takes the color coming that was given coming from the vertex shader, and basically that's a final conversion from linear sRGB to sRGB, so the colors show correctly on the screen. What is interesting here is that we're going to capture the positions and the color for our triangle. We're going to capture them from the pass asset file. We can actually automatically map shader constants to take the variables that you see there, like pass sRG, clip space positions. That's basically a matrix that is actually controllable from the asset itself. So that's kind of the connection. So you don't even have to write C++ codes to customize the value of these shader constants. That's already done for you. And now that we have the code, we need to define how to compile the shader, and that is that shader file. One thing interesting is that we're saying on the depth stencil state, we're saying, hey, this shader doesn't use depth testing. So whatever we're going to render is going to be splattered on top of whatever is there on the screen. And here's the one triangle pass. So this is a pass, and I'm going to try to see, is this blocking the screen again, or you can see the highlighted cursor?
It's blocking.
It's blocking. Okay, then I'm going to move it out of the way. So basically, at the beginning, you're saying this pass has only one slot, which is basically I only need one attachment, and that attachment is the famous render target. And this pass say when I'm going to begin, I'm going to clear the screen with 0.75, 0.75, which is kind of a light gray. That's the color. So this is the part where you're going to be able to customize later whatever color you want for the background. And also in this asset, you're saying this pass is going to run that particular shader that we already created. And then we have the data section, the shader data mappings, which maps all of these data to the shader constants. And then here where you're going to customize the location of each vertex in the screen and also the color of each of these vertex as highlighted in the comments. And one interesting thing is this pass as an asset is saying my pass class is the full screen triangle. So technically, this should have been called a triangle pass, because full screen actually only becomes full screen if you make it full screen in the way you define the positions of the vertices. So, but again, you can define if this triangle is truly going to be full screen if you explicitly define, all the screen coordinates of the clip space in its clip space coordinates for the screen. Then, of course, we create a pipeline, and the pipeline is just a parent pass that lists all of the passes it needs. In this case, you're going to see there is a section called pass request, and we're only listing one pass. And we're also connecting the color output slot, which refers to the render target. We're going to collect in with the swap chain. And there is a hard-coded name called pipeline output. If with that hard-coded name, this is something you need to know, then you're automatically drawing into the swap chain. And finally, the render pipeline descriptor says exactly what is the pass template we're going to use for the pipeline. And now we have an asset. And with this asset, we can give it well, even before doing that, we did two things here. We created a new pass called the one triangle pass, and we need to register that pass in the pass templates. We also created the pipeline, which is another template, and we also have to register. Because at this phase of this presentation, we're not doing C++. To make everything works fine, you wanna take the pass templates files from AC asset that comes with the engine, copy paste it into your project, and add these two passes at the end. And that's basically what I'm describing here. And then finally, we're going to run the editor. Before running the editor, we pass this to the command line, and now the RPI is going to take whatever was the main pipeline. It's actually going to replace it with this pipeline. And when you run it, you're supposed to see only that screen, that triangle with the clear color you specified, and so on. And now from then on, you can go back to the one triangle pass asset, and you can play fiddle with the colors of the vertices and the background, and now you have your one triangle pipeline. So this is basically Hello World one triangle that is essential for anyone who wants to work with a game engine, especially in rendering. The first question people ask, how can I put one triangle in the screen? And this basically, this is the answer. I don't think it gets any simpler than this. I don't think there is a quicker workaround than this one. And not only that, you replace the whole pipeline with your triangle. Okay, so the next question is, what happens if I want to add one more triangle? Then following what the tools we have at the moment, we can add another pass with the pipeline that renders another triangle in a different location. And what about if you want to render 3 triangles? Then I put there the Triforce Render Pipeline. It's an asset you can take a look. I'm just basically connecting 3 passes, each one rendering a triangle in a different location. The only thing that matters here is that only the first pass can clear the screen. And you will see it in the asset. You're going to see, oh, only the first pass clears the screen to the color. All other passes don't clear the screen. They just render their triangle in their location. And now you have a Triforce render pipeline. And that's all what the engine can do at this moment. So lessons to learn from one triangle. We learned that O3DE is flexible enough to ingest render pipelines and render passes in the form of assets. This can be done in C++ too. It only takes one command line argument to replace the main render pipeline with your own pipeline. Another thing important here is that the root parent pass of a render pipeline can reference the swap chain as an input-output attachment by the hard-coded name pipeline output. And finally, any concrete pass that is based on the full screen triangle pass is eligible to 3 vertices, identifiable in the vertex shader by the SV vertex ID semantics. So you're limited to 3 vertices in these kind of passes. Of course, things are going to get more interesting in the next section. But before understanding the next section, we're going to talk about the DrawListTag. So the DrawListTag is basically the mechanisms that decouples feature processors from passes. By this, I mean the feature processor. If you think about a complex real render pipeline as the main one, for example, we have shadow passes, we have passes that calculate the skinning data for animated characters, we have reflection passes, we have all kinds of passes. And sometimes the same mesh has to be used in different passes using different shaders. So to decouple the feature processors from the passes, we use the DrawListTag. And that way, the feature processor doesn't really know or care exactly what is the concrete pass that is going to render. All it does is it's using this DrawListTag to say, okay, here is the draw items or the meshes that you should use when rendering shadows. Whoever is the shadow pass, I don't care exactly what is the C++ class or anything in between. I just know there is something called the shadow pass, and here are the items for the shadow pass. Similarly, this is the items for the forward pass. So basically, the feature processor can assemble all of this data and attach a tag to each one of these draw packets and draw items. And then when the pipeline runs, the shadow pass is going to say, hey, is there a packet for me? Of course, it's going to use the shadow DrawListTag. Similarly, for motion and skinning calculation or OxGeom, every pass is going to ask, hey, where is my data? So this nice decoupling happens thanks to the DrawListTag. So basically, the DrawListTag is an address of a pass. So one more thing is that when you are designing as a developer, designing your passes and so on, even though the DrawListTag is a string as a developer, each of those tags is going to become a number, it's going to get an index. And this index allows for cool optimizations for easily filter and allow the pass system to find the draw packets for particular passes just by using this treating these DrawListTags as a bit mask. So basically, all I wanted to say here is there is a limited number of strings that you can use, and there can be 64, But from the point of view of a draw item, the draw item can only have 32 at the moment. It can be expanded, but right now it's limited to 32. So I think for the most part, this is enough for most render pipelines. And here you can see eventually on the bottom right, when the depth pass is going to run, it looks for, hey, what is my depth? What are the draw items sent to me? And the shadow pass gets its own draw items and the forward pass, and everything gets combined in the render target at the end. So now that we know that, let's talk about how to render real meshes. So basically, what we're going to do is, this is the default scene rendered by the main render pipeline, where you have a skybox, you have a shader ball, and you have a ground plane. You also have auxiliary geometry and gizmos. You also have some text on the top right showing some statistics. All of that is being done. There is always a path for everything you see there. There is a path in the render pipeline that is rendering that. What we're going to do is replace all of that with our own pipeline. And we're going to take, basically, we're not going to have a skybox, but we're going to have a clear color for the background. In this case, it's like a dark red. And then we're going to have a very simple pipeline that for each mesh, we're going to render the color of the mesh is going to be the normal data on each vertex. That's going to be assumed to be the color of each vertex of the triangle. And that's how we're going to shade all of the meshes. So you can see that the flat, because the ground, the normal is the same, everything facing up, it looks like a flat color, but then you can see a little bit more interesting coloring on the shader ball. So as I spoiled already the news, it is possible to render meshes with a write in C++. And what we're going to do is that we're going to be leveraging some parts of the material system, even though we're using some parts of the architecture of the material system. We're not really going to be using any of the default PBR materials, but we're going to use it as a means to an end to get our job done. So something interesting, though, that we gloss over when we talk about feature processors is that when the feature processors create draw items, each draw item needs a pipeline state object. This is basically, you can say, this is, my compiled shader in binary form ready to run. That means the feature processor needs to know what shader to use. Now, you can do this in C++, in your own feature processor. You can do these things, and you know exactly in C++ code what shader to load to render your draw items. But in this case, we're not writing C++. So we're going to piggyback on the mesh feature processor. And we know that the mesh feature processor works in tandem with the material system. And what is going to happen is that we have to create a material that is going to define the shader, one shader that we're going to supposed to use when this material is applied to a particular mesh. So we need to create a custom material. The only thing that truly matters, this is a very simple material. It's going to have one shader, and this shader is going to have a draw list, referring to the DrawListTag called Siggraph. That means that if there is a pass later in the pipeline looking for Siggraph, then that pass is going to be able to render our mesh. So basically, remember, we are leveraging the material system and the mesh feature processor by understanding that each shader also has a draw list in the material. And thanks to that, we can hook up everything and be able to run our custom pipeline. So this is the shader code, very simple stuff. In the vertex shader, we're gonna get the world matrix already on the object SRG. And again, I'm already glossing fast because object SRG means you need to be aware about shader resource group. but this is equivalent to in let's say in DX12 talking about this spaces or spaces for registers, or in Vulkan descriptor sets and so on. So this is kind of a nice way to abstract all of that and transform all of those spaces into what we call in C++ namespaces, which is also supported in HLSL. So basically, the system and the mesh feature processor knows what is the transform for each of these objects, and it's going to feed it into the object SRG, and that's how you know where is your world position for the particular mesh you're rendering. And then, of course, that's your classical transformation in the vertex shader for view with the view projection matrix, and you're passing the normal as one of the outputs of the vertex shader. And at the bottom, we just get from the data, we get a normal, and we say, hey, the color is going to be the normal. This is as simple as it gets. But now this is enough. This is basically the whole magic of the shader code. And of course, the .shader file, which says, okay, we're going to enable the depth stencil state. That means that our meshes, all of them are going to be rendered in the proper order. And the magic here, of course, is the DrawListTag, which is called Siggraph, that the shader says, I'm going to send my meshes, my data, to that particular DrawListTag, whoever listens to that later in the pipeline. And the next thing we're going to do about creating a material is that we're going to have created a material type. Now, in a material type, you define all of the properties of your material, which typically correlates with shader constants and resources. We don't have any properties, so we have the simplest material type that is possible to do, which only lists the shader we care about, and that's it. And a material and a concrete implementation of the material simply says, hey, I'm going to use the material type we just created. That's it. And because there are no properties to customize, this material is as simple as it gets. That's the other asset we're adding. Okay, so now we have a material. So we have not created the pipeline yet, but we have an official, well-constructed material asset. That means we can go now to the editor, we go to the shader ball entity, and we add a material component, and we can pick our own new material, and we're going to notice that the shader ball is going to disappear. And it's going to disappear because this material is sending data to Siggraph. And the main pipeline knows nothing about Siggraph, so that data, those draw items, get lost in the ether. Nothing happens there. We're about to fix that now. So now comes our pipeline. So again, we're going to do a one-pass pipeline, and this is the case of our the main pass we're going to have, which is based on the raster pass. And we need to declare two attachments. We'll say, hey, we need, an attachment for depth stencil, for depth testing. And of course, we need a place to render our meshes, which is the render target. It's called the lighting output slot. And then keep in mind, though, that the render attachment, the output already exists, which is the swap chain. So we don't have to worry about allocating an attachment for this. On the other hand, the depth attachment is optional and is unique to our pass, so we have to declare it. So just by declaring the name and the source for the sizing and the color format, just by doing that, automatically the RPI is going to instantiate that buffer in GPU memory, in this case as a transient attachment and so on. So we didn't have to write any C++ codes to instantiate these buffers in memory. And then we do a connection between the depth output and our attachment. This is important because also you could make that connection to an attachment done by another pass. So that's why it's important to, even though it's our own attachment, we still have to explicitly declare that connection. And most importantly, at the very bottom of this asset, we're saying my draw list tag is Siggraph. That means any draw item tag at Siggraph, I'm gonna render in this pass. And the pipeline. So this is the pipeline asset, one pass only. With this, we highlight our pass, and then we also connect the lighting output attachment to the pipeline outputs, which means we're gonna render on the swap chain. And finally, the render pipeline descriptor asset. And this is the one, this is the asset that we're gonna pass in the command line now. Just as we did before with the one triangle pass and the Triforce pipelines, we need to declare the new templates. So we adding our one pass template and then the pipeline, the new pipeline template, so that we need to add them. And now show time. So now we're gonna, before restarting the editor, we're gonna go back to the shader ball and the plane entities. We're gonna add the material components, and to both of them, we're gonna pick the new material, and they're supposed to disappear from the screen. Then you shut down the editor, you restart the editor, now with our pipeline, and boom, you're gonna see now rendering your meshes with your own shaders. And you will notice that you can keep adding more meshes. You can keep adding, and so long as they use the material we created, they're gonna be rendering our passes. And that's it for the first half of the presentation without getting into C++ code. Questions?
Did you mention that you have to enable, did you have to enable the material pipeline, like by adding it to the materials settings registry as part of these experiments?
No, you don't have to do any of that. That is the interesting part. The material pipeline is only important when you are really using
right, the forward pass.
The forward pass and all of those, when you are basically integrating with the PBR system and so
with
on.
the lighting, so the material system has a lighting type and a lighting type. If you're using those lighting type, which is built in. So if you were to create a new material and want to use those lighting type, then you'll have to add your material name to the material settings registry. But in this case, because you built your own, so it didn't matter. Okay, cool. Thank you.
Which is another very long, interesting, that would be a 1-week training into just working with the existing material system and your own lighting, very complicated stuff, which is eventually one day I'm going to do. But again, these are baby steps. This is what helps you understand. Like, just by knowing this, you can even go to the material system and know, okay, so each shader has its own tag which matches a pass. And now you can now reverse engineer back how the material system actually works in case you want to work with, our main pipeline and extend it and so, there is more of that. If for the curious attendant, you can continue on your own, which I'm going to cover in the next Connect, and you're going to be able how to add more passes, for example, to the existing pipeline and doing, custom stuff.
I was just going to mention that I mentioned the decoupling between the material, the lighting types, and the render pipeline. So the idea there is that you can it's very easy to add a new render pipeline without touching any material or lighting types. Or if you want to add a new lighting type, so let's say you have PBR, you don't like PBR, you want to do, let's say, toon shading, that would be a new lighting type, and you won't have to touch anything to do with the render pipeline or the materials. And the same thing, you can add a new material without having to ever touch anything to do with existing lighting types and render pipelines. So all three are decoupled, and there's a big effort that went into that because everything was coupled when we first built the render. So everything was very deeply coupled. So there was only one pipeline. It was only using PBR, and it was only one render pipeline. So So if you wanted to introduce new materials or wanted to introduce new render pipelines, it became really hard and a lot of duplication. So we ended up decoupling all those concepts. So it's a big thing.
Yeah, I think
That's it for me.
tune shading would be a good that everybody wants to is always used for as kind of a hello world material like customization. Like, okay, everybody always asks, hey, how can I do tune shading with the
It
engine? I think
would,
that would be
yeah.
a
We
nice
use
presentation.
our pipeline uses Lua to connect all these concepts. So it would be a new lighting type and a new material. And in theory, it could all be done without doing any C++. So depends on how integrated you want, right? Like if you want tune shading, but you want like, rain to work or other features to work with it, then you may have to touch some C++, but in theory, you can introduce new lighting types. And they should just be really easy to add.
Yeah. I don't know if there are questions in the chat. I don't have, I see some. Okay, yeah.
And everyone, feel free to also come off mute and ask your question too.
I have another question. Why did you have to restart the editor? In the last slide, you said you change the material and then the mesh disappears, and you had to restart the editor to switch the render pipeline. Is that just because you wanted to run?
That's a good point. I think the render pipeline, I never tried to modify the CVAR real time, but I think you should be able to, because I noticed on the material editor, I can switch, it shows me a Dropbox, the material of all of the pipelines it could find. And I noticed that with the material editor, you can, flip pipelines. I assuming with the CVAR, you can change it without having to restart. That's a good point.
As long as it is able to pick it up, you shouldn't have. Maybe it didn't pick it up, so that's why you may have to restart it. But in theory,
no. I
shouldn't
just never tried. By the way, I just never tried to replace the CVAR from the console. I think I should change that. Yeah, I think that should be.
In theory, it should just work. But
yeah. The during the Siggraph talk, the same question was brought up, and an engineer from Sky Engine said that they would fix that issue if it does exist, because they felt that you shouldn't have to restart the editor.
Yeah, I think you don't. I think it should just work even now. Like you don't have to restart. The only time you have to restart is if you are introducing either something more complex. So like if you introduced a new material that needs to work with the forward shaders, forward pass, then you may have to restart because you have to update the material settings registry to add a new material pipeline, and then that will initiate a whole bunch of like all the shaders related to the forward pass will need to recompile and load it. So that might require, but what you did was like a very simple custom pipeline that should not require in theory.
Well, it also depends because we have custom pass templates. I think you have to register those pass templates first, so that would require a change. But assuming you're not adding more pass templates, you're just connecting existing pass templates in a pipeline, you should be able just to reload the CVAR. But okay, so I think that's for me today. I'm always on Discord and on GitHub, so feel free to ping me. You have questions about this this part to the next part.
I don't think you mentioned it, but I think it's good to mention it that well, you already have a couple of passes, but the whole pass system also is flexible enough that if you have a connection of passes and you have some of those passes disabled, the system is intelligent enough to basically connect between passes that are enabled and whatever it's disabled. You don't need to say, oh, if I disconnected this pass, then I have to connect this to the other one. The system already does all of that for you. So in our main pipeline, for example, we have a bunch of passes that they're not enabled because you don't have that feature or the platform doesn't support it. And just by simply disabling a pass, all the other connection between the remaining passes that are enabled is going to just work.
Oh, nice. Thank you. Thank you for clarifying that.